Hello and welcome to the ProtoPod, the podcast for engineers, innovators, entrepreneurs, and trailblazers shaping the future. Here we dive into the cutting-edge worlds of prototyping, aerospace, rapid manufacturing, high-velocity mass customization, and beyond. I'm your host, Jordan Rose. Today, I'm excited to chat with Eric Martin, president and co-founder of MONSTR Sense Technologies. MONSTR Sense designs and sells advanced microscopy and spectroscopy equipment primarily for R&D in academic, national, military, and industrial labs. Their tools help researchers analyze next-generation semiconductors by measuring advanced properties like line shapes and material defects. Let's dive in. Welcome in, Eric, to the ProtoPod. Super excited to interview you today, have a quick chat. I was looking through the profile of your company and how you guys kind of got started, and it's very interesting. The origin stories of MONSTR Sense Technologies feel very much like the origin stories of ProtoCase. So for a little context, ProtoCase was founded by two engineers, basically frustrated with the procurement of electronic enclosures for the designs they were working on. And the rest is kind of history, pioneers in HVMC, high velocity mass custom manufacturing. And based on what I've read, it sounds like your origin stories for MONSTR Sense are very similar. Can you walk me through what that origin story is and how you kind of got to today?
Right. So I co-founded this company with Professor Steve Cundiff, who's now at the University of Michigan. This was based off of technology I developed during my PhD, and I spent my PhD as a builder. There's a lot of folks in physics that they do science on certain materials, and their goal is to really understand the material, and they take tools that exist and apply those tools to those materials. On my side, I was really a tool builder, where I built a new type of tool to be able to look at materials. And actually, the materials I looked at during my PhD were quite dull, old materials that people thought they understood everything about, and then we're saying, well, let's see if we can find a little bit more. And so there's the technology I worked in at the time, doing ultrafast spectroscopy, so using ultrafast lasers, these short pulses of light, 100 millionths, a million billionths of a second is how short a femtosecond is, and so we'll do say 30 to 100 of these. Femtoseconds is the size of a pulse. We're measuring stuff that happens at that time scale, and we take that, which is technology, ultrafast technology has been around. We take that and created something more advanced called multidimensional coherent spectroscopy. And still, even that's before my time of doing multidimensional kinds of using several of these pulses in sequence to be able to understand, disentangle what's going on in the material. And then what was really novel about the technology that I was developing and developed during my PhD was that this is now able to be put all those pulses in a single beam, and you could focus it down to a really small spot. And so we can now look at small materials. You could take small or spatially a lot of spatial variation, and then be able to do all these advanced kinds of measurements in this really small spot. And so, taking us back to sort of what was the origin? That was the technology we were developing, doing really, really niche stuff. I mean, and I can't emphasize, this is very, very niche stuff with communities of hundreds of people, not thousands. I know hundreds of people working in this kind of space. But we had this really new way of doing this, taking this really advanced thing, making it both easier and also applicable to a whole lot more samples and kinds of things. And so I was showing this off at conferences, had some people starting to copy it, and we're realizing, hey, there's some space here, like some interest in this kind of technology. Not huge interest, but some interest. And so that was really the start. And so the next step was, so after I finished in 2018, we got a small grant, basically, to build a prototype at the University of Michigan. So it's a grant to the University of Michigan to build a prototype at the University of Michigan. And so I built the first little prototype of this, took it to conferences, was showing it to folks, and we actually had our first purchase orders, first couple purchase orders for full, called Bigfoot spectrometers, which we'll hopefully talk about later what those names come from. But first couple of Bigfoot spectrometers in the first year, and so we were really bootstrapped with revenue from the jump. The other thing, actually, so our first product though, and our first purchase order was not actually a Bigfoot. It was actually the electron. Well, one of the keys that's really special about what we do. We do this ultrafast spectroscopy, which is a lot of optics. Everyone in our space is good at optics, though. So what we're actually specialized, we do this electrical engineering, kind of our radio frequency signal processing, so that we can pull out these really small signals in the presence of massive backgrounds. And so the first thing we sold was this electronics box, the University of Texas, and I was looking for a way to package it. I had my FPGA, a little electronic stuff, and I had everything sort of like bolted down to a piece of aluminum that I'd made in the machine shop. I was going, that's not pretty. I got to do something that makes this pretty. So I came across ProtoCase. So that was really what started. Is me, a physicist with no CAD experience, was able to jump into using ProtoCase Designer, and then and put together our first little ProtoCase electronics box. That was our first revenue.
Interesting. Okay, so a lot there. That was awesome. So
it was pretty long.
No, that was good. So what I hear from that is you talked about building, and that building seemed like it was a requirement for the experimentation that you were doing. So were there any frustrations that you had in what was commercially available currently that encourage you to make your own equipment? Because I know that you said there is equipment out there like it, but you kind of had to do some innovation in that space to get the fully functioning product that you were looking for to complete your research.
I mean, that's part of what being in a PhD in a lab that builds equipment is. You are working in a space where the kinds of equipment you need don't exist, right? So like to do, and for sure, I mean the full thing. So doing full multidimensional coherent spectroscopy with a single beam, those kind of tools don't exist, and there aren't many comparables. I mean, there are things that do ultrafast. There's tools for doing ultrafast spectroscopy, all of which work with large spots, and so fundamentally, none of those would work with the kinds of small spots that we needed, which was get really compatible with a microscope. And as I get into some of the things that we're doing more recently, with adding, and this has been since 2018, since 2019, adding microscopy, it's those kind of things. Doing ultrafast spectroscopy with a microscope just hasn't really been possible, because there's fundamental reasons why you have all these pulses. So I was talking about these ultra-short pulses. We use 4 of them in our MDCS. You can do it with 2 pulses, but no matter what, you got all these pulses coming in. You need to be able to distinguish them, right? So pulse 1, pulse 2, pulse 3, pulse 4, signal. You got to be able to distinguish what these are. The typical way of doing that is what's called with a nonlinear or a non-collinear method. So you basically have one pulse comes in at one angle, another pulse comes at another angle, and now you've got 2 pulses that are distinguishable, right? You can put your detector measuring one pulse, not the other one. And so then you can say, okay, I'm measuring changes of this pulse due to this other pulse, right? And you scale this up to 4 pulses, you can do the same kind of thing. If you do that, as soon as you get to where you're non-collinear, you fundamentally are incompatible with a microscope. You just can't get that down to a small spot. And so what it forces, it means that if you have a device, for instance, or if you have a defect that you're trying to measure in your semiconductor that's a few microns in size, you just can't measure it with one of those non-collinear kinds of methods. And so that was sort of the motivation for building the new technology. Now then, if you think about even component by component selection, there's been many of those things too that we've wound up engineering out. For instance, there's something called lock-in detection, which I won't get into the details of.
No, it's good.
The electrical signal processing things that we do, and there's many lock-in detectors that are on the market. You can buy them from SRS, you can buy them from Zurich Instruments, and when I started, I was using one of those. But when I was interfacing the commercial lock-in detector with my system, it was clunky. Like
Mm-hmm.
there were several points where I was at one point I would take an analog signal, I would digitize it, do some processing on it, reconvert that into an analog signal, send that into a lock-in amplifier, which would send out an analog output, and then I digitized that. It was a whole lot of A to
Yeah.
D, D to A, all this kind of stuff that just didn't need to happen. And so I was going, why don't we just do this ourselves? So that's why, I mean, pretty much all of the processing that we do takes place in a single field programmable gate array chip. And FPGAs, just plug that technology for a minute. I mean, those things are really incredible for taking, kind of labs and putting them on a single chip. Like you can take so many components and just integrate them all. As soon as there's a little bit of a learning curve on FPGAs, but once you get it, it makes your life just so much easier. And it's also made productizing
Mm-hmm.
the equipment that MONSTR Sense sells a whole lot easier and less expensive. Because now, instead of needing a whole lot of different components that we cram into a single box, we've got
One part.
one component,
Yeah.
and then a bunch of power supplies.
Yeah, no. So that's where I kind of wanted to go. Is so it sounds to me like obviously you have all these subsystems that make up
Mm-hmm.
the product that you're developing. Each of those, though, to your point, have to work within your product. So a lot of the time, commercially available components don't really work. So given that you have so many different subsystems that you have to manage, can you talk to me about how maybe rapid prototyping and quick iterations play a factor in your ability to, effectively, as a business, make changes to all of these subsystems, in a way that's financially viable?
Right. So I can talk about two things. So one, I'll start with the first products we've sold. So the first products, Bigfoot,
Mm-hmm.
Nessie. Um, so Bigfoot's our ultrafast spectrometer, Nessie's our microscope. So these are both their components. They're systems in a sense, right? There's electronics, there's optics, but they're components in the sense that we're going to drop them into a customer's lab. The customer's already going to have a laser, already
Okay.
going to have a sample, and so it is, from what I'm going to be talking about as this discussion progresses, a component level thing. And the biggest way that the rapid prototyping becomes necessary is just that, one, we, for the most part, I mean, these are expensive to
Mm-hmm.
build, and they're expensive to purchase, but they're also expensive to build. And so for the most part, we build a system when we receive an order. And there have in the past, there's been custom requirements from our customers that make it such that we really don't want to have a big stockpile of Bigfoot and Nessie supplies ready, because there might be some modifications.
Yep.
And we've also, because the numbers of sales that we're doing, and these are not, and these are big pieces of equipment. These are not things that we're selling at scale, right? We're not
Yep.
selling 20 of these a year or anything like that. And so there's some iterative design that's even happening as we're selling products. And so we'll say, learn from a customer install some sort of change that we really want to make to the next version that's
Right.
just going to make that
All of
install
them better.
easier, for instance, right? And so making things when we get the order is one of the things that we found to be very useful.
Mm-hmm.
Even when from the very beginning we buy, say, three versions, and even then we scrap some of the parts. We learned from the very first one
Yeah.
not to do that. And so that's where I think a lot of the value of being able to buy things in very small numbers, because we're selling equipment, is very important for us. And then being able to get the quick turnaround on, we've got a 3-month lead time from when we get a purchase order to when we need to deliver the product. And so to get all the parts in, assembled, tested within that time requires relatively quick lead times.
Yeah, can you explain exactly what doors or what problems, I guess I was going to say doors, that open for your customers, but what problem does your technology solve? So you mentioned that it's really great for measuring very small things. Is that something that previous to your technology was a big barrier for folks? And can you just expand on that?
Right. So let me start by discussing. There's an industry application on which we've been very focused. We're getting early customers calling us and doing service work. So using our technology for service work, and that is semiconductor inspection. And this is something that's very relatable. I'd like to talk as well about the research side of things, which is where we have generated most of our revenue. But just an application that's really you can really wrap your head around is this space we're working silicon carbide. And so in 2017, Tesla decided that they were going to use silicon carbide in all their cars. And this is because silicon carbide is a wide bandgap semiconductor. It's good for power electronics, and it is just a lot more robust and good for these applications than silicon. And so Tesla adopted it. Everybody else followed suit. And so now you have this from 2017. You have this huge, growth in silicon carbide. Silicon carbide was chosen as a couple wide bandgap semiconductors that folks are thinking about. There's silicon carbide. There's gallium nitride. Gallium nitride we also work with or measure. Is in phone chargers. So pretty much all the miniature efficient phone chargers use gallium nitride. But for automotive, big power electronics, silicon carbide won. One of the big reasons was because people went, oh, silicon carbide's got silicon in there. That should mean that a lot of the things that we use for processing silicon
they're the same. Yeah.
They're the same.
Yeah.
Turns out for inspection, that is just not the case. So silicon I don't know if you've seen a silicon wafer, it's like this gray, reflective, perfect looking thing. And they are. Silicon is grown with just incredible perfection, the crystals, so that if you look at the surface of a silicon wafer, silicon wafer, and you find any sort of a pit, a ridge, something like that, hey, that's a defect. You can throw that part of the material away. So what they use for silicon, they use what's called surface inspection. They just take white light, focus it down really tightly, scan it over the whole wafer, and then find all the defects that way. If you do that with silicon carbide, you throw away the whole wafer. I know you're like, the whole surface is trash.
Yeah.
There's nothing good here. But it turns out that most of those surface defects that you measure are not actually killer defects. And so the material is very robust to those. Two, a lot of the defects you do care about are actually subsurface, and so you don't even detect them in the surface channel. And so even if you try to, put some machine learning algorithms on there to get better at classifying the surface defects you see, you're still going to miss a whole lot of important defects. And so the whole industry shifted towards, for their optical inspection, they now use something called photoluminescence. Photoluminescence, you shine a UV laser, so basically a high energy laser on there, and then you look at the light that gets emitted at a lower energy. And this is a really good. It's an indicator. So photoluminescence, it's measuring the electronic properties of the material, right? You're able to see, hey, there's something in the electronic band structure, the fundamental semiconductor, that gives you this emission state. That say an emission state that you don't see from bulk. Nice silicon carbide doesn't have it. Your defects do. And when I heard that, I got excited because I've done a lot of photoluminescence is easier than ultrafast. Typically, from like drawing it, if you draw a figure into a paper, right? Your PL, you got like a blue laser come in, green, red light come out. Simple to sort of draw. But in practice, I always found it very annoying to do photoluminescence. It was slower. You have difficult collection efficiency. So when those photons get emitted, they go in all directions. So it's kind of tricky to collect all the photons, especially if you want to inspect a large spot. Kind of things where you want to look at an entire wafer. There's just some break in where photoluminescence works well. So it's hard to collect the signal that way. And I was going, well, I much prefer to look at these things with ultrafast lasers, because I can collect all of my signal. It's a coherent response. And so there were a whole lot of reasons that I just preferred it. So I had this hypothesis. I bet if we apply our ultrafast lasers, our spectroscopy to these wafers, we're going to be able to detect the same stuff they do with photoluminescence, but we should be able to do it faster. And there should actually be a few defects that we're able to see that they're not able to see. And over the last couple of years, that's only been validated. So we've gotten to where, and we're a small company, less than 10 of us, but we've gotten to the point where we can now use ultrafast lasers, use a pump probe kind of spectroscopy to map out all the defects over a 6-inch wafer in 8 minutes.
Wow.
So we've been able to really push it. And if you go through the numbers on this, you're talking, billions of pixels you got to measure. I mean, you're moving extremely fast here. The amount of time we have per pixel, and this is something that ultrafast folks never would have. I mean, we're used to, like, with multidimensional spectroscopy. So the thing I talked about at the beginning, which is the advanced technique. Bigfoot does this. MDCS used to take 15 minutes to an hour or so to get a spectrum.
Okay.
We got that down with Bigfoot to about, for a lot of samples, a minute, which is fast, right? But now we're talking doing wafer scale imaging, getting useful information, not full MDCS, but useful information where you have 1 microsecond per pixel. And then you got to move on to the next pixel, or else you're never going to finish your wafer scan. And so anyway, what's been exciting about this is that with a small team, we've been able to demonstrate we can measure the same defects that you see in photoluminescence, plus a few others. And so that's been, I'd say, the real value proposition that we've identified and validated.
Yeah, so you're really at least an order of magnitude, if not 2 orders of magnitude. Like, you're substantially quicker right now and only moving forward. And for So then other ultrafast, then photoluminescence microscopy. Okay. There's some incredible engineering that has gone into doing photoluminescence at scale for silicon carbide. We are actually still, so our method is about a factor of 2 slower than the state-of-the-art PL microscopes. Yes.
That said, that there's some engineering that's going to get us moving above and beyond that. I mean, we're nowhere near our fundamental limit, whereas PL really is. PL has been engineered to its limit. And then there's a few other benefits that ultrafast gives you. That's what I was going to ask. So there's one of them. This maybe gets a little bit niche, but one of them. So basically, the way silicon carbide's grown, you grow, and this is with any of these wafers, right? You grow an ingot, or in silicon carbide, say it's a boule. So you grow a little boule, you slice that up into wafers of a substrate. And that substrate, you're gonna polish that down, make that look really nice, and then you're gonna grow an epitaxy of, say, 8 microns, a thin epitaxy on top of it. And the epitaxy is going to convert some of the defects that you have in the substrate into non-defects. It's just going to give you a nicer surface on which you can then pattern devices. PL is pretty good at measuring the epi. So after you've grown the epi on top of it, it's pretty good. The substrate really doesn't supply any good information about the defects that are in the substrate. We've found that we measure with ultrafast all the same defects in epi as you measure with photoluminescence, but we also measure the defects in the substrate. So we've done that comparison with. So then basically to compete with, so you do the same thing that our tool can do. You have to do X-ray topography. X-ray tomography on the substrate, right, and then do your photoluminescence imaging on the epitaxy. Okay. Ours can really do both of those
all simultaneously.
That's one, which is just saying, hey, these are some new kinds of defects that you can measure. This is an optical way. Optically is oftentimes easier than, and in this case, it is easier than using X-rays and faster. But it's an optical way to look at these substrates. Number 2 is, so it being I was talking about, I got all these pulses. It means it's nonlinear. So it means that actually the signal that we measure depends on pulse 1 and pulse 2, or pulse 1 and pulse 2, 3, 4. However many pulses you use it. The signal depends on all of those pulses. Nonlinear means that you need a really, really high intensity in order to get a signal. And so if you focus your light down to a very small spot, you're only going to get signal from the focus. And now, that may, in the lateral direction, that may sound trivial. Like any microscopy is going to give you signal from that. But also, this works in the Z, or in Canada you'd say the Z direction, right? So your depth sensing, you're also going to get high spatial resolution there. And so what we're able to do that photoluminescence cannot do is volumetric scans. So we can actually scan into the material, we can scan through the material, and so we can say measure defects in the surface at the epitaxy. We can measure the interface between the substrate and the epitaxy. We can measure where defects are actually converting from defect in the substrate to defects in the epitaxy. We can scan all the way to the back. We can look at the bottom of the substrate. We can go anywhere in there, and then so do these steps. So you can actually take, say, a thicker piece of substrate before you've even sliced it, and start to characterize through the entire substrate. So that's another advantage that ultrafast microscopy has over photoluminescence, is that you get this new sort of resolution in that Z direction.
Yeah, so you're really opening up a lot of opportunities for the end users, the industrial users, to update their processes potentially through maybe inspecting something before it's sliced, or after it's sliced, getting a more complete inspection of the product, so that they can maybe improve their engineering process of actually growing the substrate. That's actually very interesting. I can absolutely see the application, and obviously, like as you mentioned, your goal is to get that speed up to the theoretical limit. So to be able to do that in a time that is less than the conventional method would obviously be a game changer in those applications. You also mentioned off the start there that was the industrial application, but there was also research application. Can you expand on what that is?
Yeah, so the research applications really comes from why do we build the multidimensional spectrometer in the first place? And it is because, so multidimensional coherent spectroscopy, again, this is a community that's got hundreds of people in it, not thousands, not millions, hundreds of people in it. There's a lot of new information you can get out of materials using a multidimensional, or MDCS, I'll just shorten it to that, using MDCS. And so for instance, one of the things that we're doing is we're correlating, say, absorption energy and emission energy, right? So the sample's going to absorb at some wavelengths, it's going to emit certain wavelengths of light. If you correlate those, there's a couple things you can do. One, you could look at coupling, right? So say, basically, I can say, hey, I got this one energy level is absorbing light, but then another energy level is emitting light. Therefore, I have some sort of a mechanism in my material that is coupling those two. And so say you can look at a heterostructure, a semiconductor where you have different layers, right? And you could say get absorption at one layer, emission at another layer, and then we can directly measure what's the coupling between those two layers of semiconductor, as an example. And so this is something that fundamental researchers and folks who are making new semiconductors and trying to understand how those devices work and how well they've been fabricated, this is something they can use. Another thing you can do with it is you could look at what we say is homogeneous properties in the presence of inhomogeneity. Now, that was a lot of big words that basically the best example I like is quantum dots. Quantum dots are these little tiny, tons of applications folks have talked about, solar cells, tagging things for measuring things in the body. But anyway, so quantum dots, the size of them determines what wavelength they're going to absorb and emit.
Okay.
And so if you grow an ensemble of quantum dots, there's going to be some size variation. And so if you do spectroscopy of an ensemble of quantum dots, you're going to measure some line width, right? There's going to be some various versions of red or various versions of green over some range. That line width is always limited by the inhomogeneity, the size distribution of these quantum dots. If you take a method that is capable of correlating absorption and emission, right? So that means you're only going to absorption and emission from a wavelength if those two are coupled, right? Then what you can do is you'll find that if you do this kind of spectroscopy on an ensemble of quantum dots, is each quantum dot will absorb and emit at its energy. And so you can, by unfolding this into two dimensions, you'll see that there's a diagonal distribution corresponding to the inhomogeneous line width, but then an off diagonal distribution, which really corresponds to, this is where absorption emission, it's the homogeneous line width of a single quantum dot. And so that's one of those that, again, hundreds of people doing it, but if you have something where there's inhomogeneity, and this could be fluctuations in the thickness of your semiconductor. This can be, you know, motion in an ensemble of atoms. And there's a lot of different places where you get what's called inhomogeneity. Um, but in semiconductors, that's kind of the code. In quantum dots, then, so the thing you can do is now, so you've got this like really narrow line width corresponding. You can like look at basically the properties of a single quantum dot, despite the fact that there's all this broadening due to all these other quantum dots. You can look at, okay, what's one, and you can look at phonon sideband. So say this one quantum dot, it like vibrates with certain energies. You can pull those things out, even if those phonon sidebands are a lot smaller than the inhomogeneous line.
Right, so they're able to filter out the error basically in their measurement, which allows them to develop new methodologies for, creating or designing these things. It's fascinating. There's so many applications. I wonder, you had mentioned obviously your Bigfoot product. That sounds like it's very near and dear to your heart. You've developed that with your team. Can you talk to me about that sounds to me like a very complex task. You're on the cutting edge of science. How has the I guess the project development and project management process worked at your company, given that you've got it's not just you in a lab now, where you're
right.
Plugging away and figuring it out, and you can ask people, but now you're leading a team and ensuring alignment on where you guys are headed on a very complicated piece of equipment. What has that been like for you?
So the Bigfoot was a lot simpler.
Okay.
Our more recent Kraken, which I'm going to talk about in a second, and I've kept alluding to, that's the full system, has been challenging, and it has strained us. We've learned new things.
Okay.
Bigfoot, the way that's worked is there was always kind of each project had one person was really in charge of that whole thing, and so I made this prototype of Bigfoot. And again, like I said, not good at CAD, but I did actually the first one. I made some version of CAD, and I machined my own base plate for it.
Nice.
But brought in. So our first hire was an engineer, Alex Valentine, who she's just an incredible CAD whiz, and so she came in and sort of redid that Bigfoot base plate. Proper CAD procedures, made a lot nicer of an easier to use thing, that easier to modify, easier to align. Everything about that second version of Bigfoot was so much better. And so she was really in charge of all of the CAD. So that being the base plate, getting all the optics into the right spot, designing the enclosure around it. So she was in charge of all of that. And at that time, there was just the two of us. So then I was in charge of the electronics. As things have progressed, like folks have grabbed more things, say software has shifted, who's in charge of the software and all those, but it's been mostly, one person in charge of all. With Kraken, however, so Kraken is this new product we just released at the end of last year, and released the Kraken. And so Kraken is a full system that really integrates all of these component level products that we have into a single thing. So it's got a laser that we don't make our own lasers, so we've a laser that we've purchased, integrated underneath this table. It's incredibly small footprint, with a little foot. It's a simplified Bigfoot is what's in the big Kraken system, and it's got a Nessie microscope in there, and then a big sample compartment. The whole thing, it's huge. ProtoCase did make the enclosure, manufacture the enclosure for us. Alex designed the enclosure. ProtoCase manufactures this enclosure. It's huge thing. Size of footprint of a desk and 5 feet tall. But anyway, so that we've now had a whole lot of hands that are on that, from testing to make sure that all of these components are going to work in the lab. So on a breadboard table, getting all the components working together, seeing how that's going to work. There's firmware on there that's needed to evolve along with the software. We try to keep one set of hands on that at a time, but there's a few of us that work on that and are passing that around. Then of course you have all the hardware components, and there's additional hardware components that have been engineered between the laser and the little foot, between the little foot and the Nessie. And so it has been challenging. Where there's been certain points where we've made some missteps, right? Where there was some communication that was lost, and next thing you know, you're going, this laser doesn't fit.
Yeah.
For instance, was one of the first things that happened, where there was just a difference in CAD of the laser versus what the system actually did, and next thing you know, laser doesn't fit. And so for managing those things, I mean, there's been a couple things that have happened. One, we're learning to improve our processes to make that communication more reliable, to ensure that those sorts of handoff communication errors don't happen as often. And then the other one is, which I think is where companies like ProtoCase and our machine come into place, is being able to quickly design and correct for those kind of mistakes that happen, right? And so again, Alex, CAD Whiz can very quickly make design an adapter plate or something that's going to be able to shift the laser position, or be able to we'll modify something so we can get some mirror over there to be able to move. There's a lot of things that we've learned how to do there, but definitely there's been growing pains in terms of figuring out how to get communication right between each of us working on our own projects.
I mean, it only
at the system level.
It only makes sense, and thank you for that allowing us to contribute in a small way. I mean, that's really what we look to hear from our customers. We really think that our HVMC, or high velocity mass custom, allows for mistakes like that, because that is the development process when you're innovating, right? Those things are going to happen. And whether it be us making a sheet metal enclosure, or us making machine parts, or 3D printing, whatever, we look to alleviate that pain in customers, because we know that exists. So no, that's great to hear. I did want to ask, so obviously this is as you've alluded to, the Kraken system has much more going on. The Bigfoot system probably integrated into your customers' current equipment, and where this is a more all-encompassing solution. Why is that important to your customers? What difference does that make for them?
It actually it's important to a different set of customers. So
okay.
the Bigfoot, and that's really where and one of the things that I'm always want to sort of evangelize whenever I'm talking to anybody about entrepreneuring and whatnot is customer discovery. Customer discovery is something that of course, when I was in grad school, didn't know anything about. But as soon as I started taking the first class on entrepreneurship and getting involved in some of the programs that NSF offers, customer discovery was pushed like, hey, you need to learn about the voice of the customer. You need to learn about value proposition. You need to learn that you are making a solution to a problem. And the first thing you need to do is figure out what is the problem. And so that's motivated most of the things that we've done since we'll probably right after deciding that we were going to start a company.
Yeah.
we did decide we were going to start a company around Bigfoot before really doing much customer discovery, besides going to conferences and seeing, hey, people want this. If we'd done too much customer discovery on just the Bigfoot, we probably wouldn't have done it at all, because we realized the market's too small to grow anything. But since then, I mean, my focus has been, it's actually been a great market to grow with, right? Because the customers have been phenomenal. They introduce new ideas, new like systems, semiconductors that they're working on. But it is not a market that could sustain a growing business.
Yep.
And so the way that you do that is through, you basically find people that are working in the space and you ask them what their problems are. And you want to hone it in on an area where you think you can help them with solutions, but you're not presenting any solutions. You're just listening to problems. And so with our Bigfoot spectrometer, we solve problems of people who are already working in the ultrafast space. They already have an ultrafast laser. These are scientists who are maybe, scientists at academic labs, maybe military labs, national research labs, but these are really scientists trying to understand these problems who already have a laser. Once we started, expanding that circle to include, material scientists or semiconductor fabs,
Yeah.
right? At that point, they don't have an ultrafast. They may have an ultrafast laser, but they don't, build all that stuff on there. They want to just buy a solution that solves a problem.
Mm-hmm.
And as we decided that we wanted to become a company that solves problems, doesn't just make components, we knew we need to build a system that takes it so that someone with a problem, someone with a semiconductor wafer with defects on it, and they don't know where the defects are, can solve that problem with our tool and without having to, learn all the other stuff and build a piece of equipment. Mm-hmm. And so that was really what motivated, getting into systems level engineering and making a tool that is a full system, like what the Kraken is. And so it expands our market to include user facilities. So this is biologists can use the Kraken, material scientists can use the Kraken, semiconductor R&D labs can use the Kraken, and eventually we'd like semiconductor fabs, so doing semiconductor inspection, to be using a Kraken Gen 2.
Nice. That's an excellent explanation. I think that very well said. That really the solution focused. So finding out what the customer's problems or pains are, and then building a solution for it is I think great advice for anybody listening who's maybe looking to start their own business in whatever field they're in. My next question is looking forward. So we've talked a lot about what you guys have done. What excites you most about the future of MONSTR? Like, where do you see yourself in 5 years?
I mean, that's the real big one that I'm excited about, and this is hopefully shorter term than 5 years, but is getting to where ultrafast microscopy, which is really something we've pioneered, is being used in an application space. So really, and the one where we're targeting is silicon carbide fabs right now. But we're looking at, there's other materials and spaces that we're looking at. Gallium nitride, there's some sort of the quantum materials space where folks are actually making wafer scale devices, using a lot of like optical chips. So say doing optics on a chip. Mm-hmm. And so being able to inspect those, but I'd say that's really where I want to see this technology going, and with silicon carbide, I just see a very clear path to where the technology could be, because the challenge for and I heard this from the beginning, people saying, there's not really ultrafast lasers. Ultrafast lasers are used for manufacturing at in fabs and for etching. Mm-hmm. So ultrafast lasers are used there, but ultrafast lasers have not gotten any sort of industrial application for inspection, for doing measurements. Mm-hmm. And that's something that as someone who's an ultrafast spectroscopist, it's a shame. But of course, as a need seeker, I don't want to force that on somebody who doesn't need it. But we're finding applications where it is necessary, where it is something that it gives you additional value that simpler methods do not provide, and so that's where I'd really love to see MONSTR Sense is providing ultrafast lasers and ultrafast microscopy for real applications. And so the big one again that we're focused on right now is silicon carbide substrate and epitaxy inspection, but I do see more applications growing, particularly there's sort of two ways in which those applications grow, right? One of them is through the investigations that we do in-house, so through customer discovery leading to service work, where an industrial customer sends us a wafer that we're going to measure and return with, hey, this is the type of data that this method can provide. Mm-hmm. And then the other one is actually through our customers. So our customers who are building the next generation semiconductors that are going to be used in 5-10 years, as they integrate our technology into their process development, into the measurements that they do of devices that they're developing. Mm-hmm. As those devices transition into scalability, our inspection
we'll go with that.
We'll transition with them.
Yeah. Very exciting. Folks listening who may be looking to find MONSTR Sense Technologies, where could they find you? Where, if they wanted to chat with you about this technology, where would they reach out?
So definitely our website, monstersense.com. That's monster without an E. So it was an acronym. Yeah. But then, of course, LinkedIn as well is great. So my name's not that. Will you link that onto the
Absolutely
podcast? Or?
Yeah.
Okay, that'd be great because my name's Eric Martin, and there's a lot of us.
Yeah.
Eric Martin with MONSTR Sense should be a little bit. But yeah, I'm happy to respond to emails and messages that way.
Awesome. Well, Eric, thank you for coming on and providing us all the exciting details about ultrafast spectroscopy. Easy for me to say. But that was a super fascinating conversation, and I can't wait to see where MONSTR Sense and the technology goes in the future. And when you get Kraken Rev 2 built, and you want to come on, if you want to discuss what it's doing and how it's helping your customers, you're always welcome on the show. So thank you so much.
Thank you. That'd be fantastic, and thanks for having me. This has been a lot of fun.
Awesome. Thanks, Eric. Bye-bye.
All right, bye.